Hey guys, so in this video I want to describe a concept that pops up a lot in the actual quantum hackathon challenges that are from previous years, and also is a key concept in quantum mechanics itself, and that is the Hamiltonian. Now, the Hamiltonian is an operator that is both unitary and Hermitian. Now, unitary is kind of like all the other operations we've talked about before, and Hermitian just means that this Hamiltonian matrix is going to be the same as its conjugate transpose. Now, the information that Hamiltonians give us are mostly twofold, and that is the total energy of the system. So if we apply this to any quantum state vector psi, we will get the total energy of the system. And also, in some cases, it describes the time evolution of the system. So how the system evolves over time. Now, how do we actually find the total energy? Well, before I do that, let me explain the decomposition of what total energy is. You may remember from mechanics, it is just the sums of the kinetic, T, and V, potential energies. Excuse me. Now, where the Hamiltonian comes into play in actual Ket and Bra notation is if we apply it to some quantum state vector, psi, any sort of psi. Now, this gives us unique information about the energy, Ket psi, of the same quantum state vector. Now, this energy is some real number, which corresponds to two things, what we call, or two names for the same thing, what we call either the stationary state, so the energy at one fixed point in time. We also call this the energy eigenvalue. You may remember the term eigenvalue from differential equations or linear algebra, depending on how far that went. And this describes the energy in a fixed state, a fixed point in time. So let's say you measure a quantum system at this point, and it has energy at this point in time. Now, if we want to do evolution over time, that just brings in another factor. So your energy at that fixed point in time then transforms, if we're going from a stationary state, to e to the power of I e t over some constant. Now, t is moving, e is your previous energy, and I is your imaginary number. Now, this has a negative sign. Now, the specifics of this aren't really relevant, but just know that the Hamiltonian as an operator represents the total energy of your system and how it evolves over time. And it can be thought of as a solution to this equation here. Now, let me give you an example that I think will help explain Hamiltonians in a lot easier way in terms of the qubits we've been talking about before. So let's say we have an electron, any sort of electron. Now, this electron can have a spin up and a spin down corresponding to two quantum states, Ket 0 and Ket 1. Now, let's say this electron has a Hamiltonian equal to negative omega over 2 z. Now, z is our unitary operator, our unitary Pauli matrix that we've talked about before, and omega is just some frequency. We can think about omega as the strength of a field an electron is in, and that's why it has some evolution over time. So let's say we apply this Hamiltonian operator to an electron that is in a Ket 0 state, and we want to know its energy. So if we just apply it to the Ket 0 matrix, which if we remember is 1, 0, then we get negative omega over 2 get 0. Now, this omega over 2 is our energy, or our stationary state. Now, if we do the same operation to get 1, that gives us positive omega over 2, get 1. And feel free to do the math yourself using what the definition of z is. Z, in this case, is just equal to 1, 0, 0, negative 1. And this is another energy, or another energy eigenvalue, the solution to this equation here. Now, you may notice that this energy is higher than this energy. And this means that this energy is lower than this energy, because this energy is negative and this energy is positive. Now, we call the lower energy, in this case, the ground state. And that's a universal term in whatever kind of quantum computing context you want to talk about. The lowest energy eigenvalue is called the ground state, and finding it is one of the central goals in quantum physics and quantum computing. So yeah, normally in quantum computing, these types of Hamiltonians are built as compositions of operations. So let's say we have a Z and an X Pauli matrix, for example. Now, these types of operations are something that happen at an instant in time, but they are unique types of operations. So the idea of the Hamiltonian is that they are operations that happen on a quantum state or a qubit in time. And they give you information about the energies of that qubit, which in real life manifest as different things, such as an electron in an actual quantum computer. But the main idea is Hamiltonian, total energy, and time evolution. And the solution to this equation gives you energies in stationary states. So yeah, thanks for watching, guys. Bye.